Off the coast of Fujian province, there is a machine so large that pilots flying overhead can spot its shadow moving across the water. It is not one machine. It is hundreds of them, spinning together, breathing together, adjusting themselves in real time like a single living organism spread across the sea. Engineers call it a wind farm. But what China has built goes so far past that word that visiting energy experts have started calling it something else entirely. A living giant. Not because it has a brain, but because it behaves like it does. It senses the wind before it arrives. It shifts its own blades to catch gusts other turbines would miss. It talks to itself, thousands of sensors passing data between machines faster than any human could track. And it produces enough electricity in a single year to power a city the size of Amsterdam, using nothing but ocean wind. If you like videos like this, please take a second to hit the like button because these take a ton of work to put together. And subscribe so you do not miss the next one. What you are about to see will change how you think about what a wind farm actually is. We are not talking about a field of spinning blades anymore. We are talking about a coordinated machine the size of a small country, and by the end of this video, you will understand exactly why engineers who study it keep reaching for the word alive. The scale nobody expected. Let's start with size because the numbers here do not behave like normal wind farm numbers. This offshore installation stretches across more than 400 square kilometers of open water, an area larger than some small nations. Inside that stretch of ocean sit turbines so tall that their blade tips reach higher than most skyscrapers, spinning at the end of towers driven deep into the seabed. A single one of these turbines can power thousands of homes on its own. Multiply that by hundreds of turbines working together, and you get a facility capable of generating several gigawatts of electricity, enough to replace multiple coal power plants running around the clock. But raw size is not what makes engineers stop and stare. Plenty of wind farms are big. What makes this one different is how the turbines are built. How they are placed, and how they behave once they are switched on. Each blade on the largest turbines here stretches longer than a football field. Picture standing at one end of a soccer pitch and being unable to see where the blade tip ends because it curves out of sight. These blades are not rigid metal bars. They flex, bend, and twist slightly with every gust, engineered from carbon fiber composites, light enough to spin freely but strong enough to survive typhoon-force winds that regularly batter this coastline. A blade that long generates enormous force at the tip, which means the entire turbine, from the foundation buried in the seabed to the nacelle housing the generator, has to be engineered as one continuous system built to survive forces that would tear apart a normal structure. A group of German offshore engineers who toured the site reportedly described the blade manufacturing process as closer to aerospace wing construction than typical turbine assembly. That comparison is not an exaggeration. The tolerances involved in shaping a blade this long, keeping it balanced so it does not wobble at high speed, and keeping it light enough to spin efficiently, push right up against the same engineering limits used in building aircraft wings. Building on water that does not want to hold still. Here's the problem nobody solves easily. You cannot just drop a 200-meter tall structure into the ocean and expect it to stay upright. The seabed off this stretch of coast is a mix of soft sediment, shifting sand, and in some sections, solid rock that varies wild depth from one spot to the next. Every single turbine foundation has to be custom engineered for the specific patch of seafloor beneath it. For the turbines standing in shallower water, engineers drove massive steel monopiles, single hollow columns wider than a subway tunnel, dozens of meters into the seabed until they hit stable rock. For turbines further out where the water runs deeper, monopiles alone would not survive the wave forces, so the design shifts to jacket foundations, four-legged steel lattice structures that spread the load across a wider footprint, similar in principle to an oil rig but engineered for constant rotational stress rather than a stationary platform. And in the farthest, deepest sections of the farm, the engineers went a step further, floating the entire turbine on a semi-submersible platform anchored to the seafloor by mooring lines, instead of a rigid foundation at all. A floating turbine that generates power reliably while bobbing gently in open ocean swells is one of the hardest problems in renewable energy right now, because the platform has to counteract its own movement in real time to keep the blades spinning at a stable angle into the wind. Get that wrong and the whole turbine becomes wildly inefficient, or worse, dangerously unstable. Building any one of these foundation types is difficult. Building all three types in the same wind farm, choosing the right one for each individual location based on seabed surveys, is closer to running 3 separate engineering projects at once than building one wind farm. A skin that senses everything. This is where the living giant description actually starts to make sense. Every turbine here is covered in sensors, hundreds of them per unit, tracking wind speed, wind direction, blade vibration, internal temperature, and rotational stress every fraction of a second. That data does not just sit inside each turbine. It streams continuously to a central control system that treats the entire wind farm as one connected network rather than hundreds of separate machines. Think of it like the nervous system in your own body. When wind shifts direction on one side of the farm, turbines in that section adjust their blade pitch and nacelle orientation to catch the new angle before a human operator would even notice the change happened. When a storm front approaches from the open ocean, the system does not wait for each individual turbine to react on its own. It begins adjusting turbines on the leading edge of the farm first, feathering blades to reduce load, while turbines further inland keep generating at full capacity for as long as safely possible. A visiting Danish wind engineer whose country pioneered much of the offshore wind industry decades ago reportedly said, "Watching the control room dashboard felt less like monitoring a power plant and more like watching a flock of birds shift formation in real time." That is not a small compliment. Denmark essentially invented offshore wind engineering, and even their experts walked away describing this coordination system as something beyond what their own farms are capable of. The system goes even further during typhoon season, which this stretch of Chinese coastline experiences regularly. Instead of simply shutting down when a storm approaches, the turbines rotate their entire nacelle to point away from the oncoming wind, reducing surface resistance and stress on the blades, essentially turning their backs to the storm, the same way a person might turn their shoulder into a strong headwind to reduce how much force hits them directly. Once the storm passes, the system brings turbines back online in a coordinated sequence rather than all at once, protecting the electrical grid from a sudden surge of power hitting it simultaneously. The robots that maintain a giant A structure this size, sitting in salt water, batten constant humidity, and facing regular typhoons, would be a nightmare to maintain using traditional methods. Sending human technicians out by boat to climb each individual turbine is slow, expensive, and dangerous, especially for the turbines sitting furthest from shore in rougher water. So this wind farm uses a growing fleet of autonomous maintenance robots. Some crawl along the blades themselves, inspecting for microscopic cracks using ultrasonic sensors long before those cracks become visible to the human eye. Others are underwater drones that inspect the foundations below the waterline, checking for corrosion or marine growth that could weaken the structure over time. A separate fleet of surface vessels, largely autonomous, ferries components, and smaller repair parts between turbines without needing a full human crew for every trip. This matters more than it might sound like at first. A single blade crack that goes unnoticed for months can eventually cause catastrophic failure, sending a fragment worth thousands of dollars crashing into the ocean, or worse, damaging the entire turbine beyond repair. By catching problems at the microscopic stage, the maintenance system keeps the farm running at near constant capacity instead of losing turbines to unexpected failures. One maintenance engineer describing the inspection drones to a visiting energy journalist compared them to white blood cells patrolling a body, constantly circulating, constantly checking, catching problems before they can spread. Feeding the mainland grid, generating electricity out in the ocean is only half the challenge. Getting that electricity onto land, into a stable grid, without losing huge amounts of power along the way, is its own engineering fight. The wind farm connects to shore through massive undersea cables, some running for dozens of kilometers along the seafloor before reaching converter stations on the coast. These are not simple cables. Offshore wind power comes out of the turbines as alternating current, but sending alternating current over long undersea distances loses a significant percentage of power to resistance along the way. So the farm converts its power to high-voltage direct current before sending it to shore, a process that requires massive converter platforms sitting out in the ocean, essentially small industrial buildings on stilts, doing nothing but transforming one type of electrical current into another before it makes the trip to land. Once on shore, a second converter station switches the power back to alternating current so it can feed directly into the regional power grid. Building and maintaining converter platforms in open ocean is its own specialized branch of engineering. Saltwater corrodes electrical equipment quickly, so every component inside these platforms is sealed, pressurized, and climate-controlled to keep moisture away from sensitive electronics that would otherwise fail within months. A team of French grid engineers who studied the converter design reportedly noted that the redundancy built into the system, with backup converters ready to take over instantly if a primary unit fails, exceeded what most European offshore projects consider standard practice. Living alongside the ocean, not fighting it. One of the more surprising parts of this project is how much effort went into making sure the wind farm does not damage the ecosystem it sits inside. Early offshore wind projects around the world faced criticism for disrupting fish migration patterns and seabird flight paths. Engineers here studied years of marine data before finalizing turbine placement, spacing units to leave clear migration corridors for fish populations that move through this stretch of coastline seasonally. The foundations themselves, strange as it sounds, have become something close to artificial reefs. Marine life has started colonizing the underwater sections of the jacket foundations, with mussels, coral, and small fish populations establishing themselves around the structures within just a few years of installation. Divers who have inspected the foundations report significantly more marine biodiversity around the turbine bases than in open stretches of seafloor nearby. In a strange way, a structure built to generate clean electricity has also become an accidental habitat, turning empty ocean floor into a thriving artificial ecosystem. Bird strike risk, a major concern with any large wind installation, gets addressed through radar systems mounted on select turbines that track incoming bird flocks. When a large flock approaches during migration season, the system can temporarily slow or feather blades on turbines directly in the flight path, reducing collision risk without shutting down the entire farm. What this actually means: put all of these pieces together: the blade engineering, the custom foundations, the sensor network acting like a nervous system, the maintenance robots, the undersea power conversion, and the ecological integration, and you start to understand why engineers keep reaching for that word: alive. This is not simply a field of turbines someone bolted to the seafloor and connected to a grid. It is a coordinated, self-adjusting, self-monitoring system that behaves less like a static piece of infrastructure and more like a single organism spread across hundreds of square kilometers of ocean, constantly sensing its environment and adjusting itself in response. The output numbers back up the ambition. A facility of this size can generate enough electricity annually to offset millions of tons of carbon emissions compared to an equivalent coal plant, while providing stable power to a region that has historically depended heavily on imported fuel. And this is not a finished, static achievement either. Additional turbines are still being added to the outer edges of the farm, extending its reach further into deeper water using the floating foundation technology, meaning the living giant is still growing. For a country that entered the offshore wind industry years behind early pioneers like Denmark and the United Kingdom, catching up this fast, and in some technical areas surpassing the engineers who invented the field, says something about how quickly this kind of infrastructure can now be built when resources, coastline, and manufacturing capacity all align. This wind farm is proof that renewable energy at this scale is not a distant future concept. It is already running, already powering cities, already growing larger every year. If this deep dive into China's living wind giant blew your mind, hit that like button, subscribe, and turn on notifications so you never miss the next one. There are more videos on the screen right now if you want to keep exploring. So here's my question for you. Would you want a wind farm like this, built off the coast near where you live? And do you think the ocean ecosystem benefits are enough to outweigh the concerns some people have about offshore construction? Drop your answer in the comments below.